Okay. So yesterday we introduced rolling motion, which was a combination of pure rotation and pure translation. Okay, and this gave us our new rotating motion. So basically chapters 1 through 9 plus chapter 10 equals chapter 11. That's the way to look at it. And we saw some interesting things energetically. The main one being that there were two forms of energy. You had potential and, or not potential, you had translational and rotational, right? And we also saw that because the velocity is 0 at this point, there was this force of static friction. However, so again, the velocity is 0 at point P, so the wheel is not slipping. So the static friction means that it's even though the wheel is moving and rolling, so you might think, well, it's kinetic, but this static friction prevents it from slipping. So it's preventing a motion. It's static. The velocity down here is 0. As you saw with the picture yesterday, picking the direction of the static friction is not quite trivial. You'll notice that whether it's going up or down, you have to identify physically which direction you're slipping against, and then pick that direction. All right. So as you're rolling down, there'll be a tendency to slide down the ramp. The static friction will oppose that sliding. All right. So let's see here. So we had some of these equations that we could look at for the center of mass for a yo-yo and a ramp. These can all be derived from summing the forces and then summing the torques. So we're not quite at the point of summing the torques, but if you do a torque and force analysis, these center of mass equations come out. And I'll leave that as an exercise to you, because they're not hard, and it's good for you to do some of these. And we have more sort of important fish to fry. Where we left off was looking at sort of torque in general. Now, what do we mean by torque in general? So I introduced you to the main expression for torque, which I'll write here. There's no reason not to put it on this slide. They're just being a little silly. Which is that torque equals R cross F. All right, which was kind of obvious from what we saw previously. This is chapter 11. In chapter 10, they just wrote it, they just said that the magnitude of the torque is equal to R F sine phi, which if we were paying attention from chapter 3, this generalization is fairly obvious. What isn't obvious though now is in chapter 10, we only had an axis of rotation. Now, torques don't need to necessarily be rotating, but they can be found about a point. All right? So as this object moves along this force, along this straight line path, it will have different torques about the origin as it moves along. Okay? So torque still requires you to have a point, but it need not be a fixed rotation, which can often throw students off. And then, of course, we have our dreaded direction determined by the right-hand rule. Now, this can get complicated and lead to craziness. So I want to, when we go through the checkpoint, which is where we're going to start in a minute, I want to show you how the cross products of unit vectors work, and then how you can use your right-hand rule to verify them. Because the right-hand rule is sort of easy to do, but if you're not sure, sometimes you don't want to trust things, and there is a mathematical way, a very easy mathematical way to look at cross products. And so I'm going to teach you that, and then we're going to use that to evaluate the checkpoints and see if we can find the error in part C, and then see if we can get it. I think they incorrectly rotate their axes in a way that where they do they think they're doing a rotation, but they're really doing a reflection, and then everything goes caca. Because that's the only way I get the answer they get. So once you do this, you can see we sort of expand to our more general definition of torque, and we get our chapter, which I've been writing for the last couple chapters, but we also have our chapter 10 definition. And then you have torque in terms of the moment arm and the line of action. All right, so these are the perpendicular component of F or the perpendicular component of R, but in your engineering courses, you will likely see torque written this way. Now, I encourage you to always remember, if confused, all right, this is sort of my Professor Toland will help you cheat statics. So every statics, I have seen statics students in many schools, well, not many schools, but the schools I've been to, and at LaGuardia talk about get just thrown for a loop in torque. And in fact, Professor West and I have conversations where he yells at me and says, oh, the students don't do torque. And I yell at him, and I'm like, they darn well do torque. So if you're ever confused by what your engineering book says, you can always come back to this definition. And I say that because you'll almost always be given the force in R. And it can be a tedious problem, but it shouldn't be a hard problem. All right? There's a difference between those two. So always remember that. When you have a bunch of torques you have to add up, it's not hard. It might be tedious, but it's not hard. And you should be able to get through some of the more difficult parts of statics. And in fact, we're going to do a chapter in statics because you'll see, well, you'll see that that torque problems are not trivial. All right, but if you have the machinery to solve them, they just become tedious, and you'll become better at picking rotations and pivot points. Okay, so let's get on to this dreaded checkpoint here. So it says the position R of a vector points along the positive z-axis. All right, so R is equal to R k hat. All right, so now we have torques. So for A, the torque is going to be 0. For B, it's going to be in the minus I hat direction. And in C, it's going to be in the negative J hat direction. Okay? So we can see that. Now, you could draw an axis and use your right-hand rule. That's more than fine. And if you do that, these two become pretty obvious pretty quickly, right? So if we draw X, Y, and Z, right? If it's 0, so we know that T equals R cross F. And if the torque is 0, right, F, in order for R hat and F hat to cross to be 0, F has to be in the K hat direction, right? It can be plus or minus, but whatever. K hat direction, okay? They may insist on positivity, but it doesn't matter. So now, if you do the same thing, we'll call this Y, this is Z, X, all right? And if you do the same thing, so it says here, you're in the negative X direction. So you'll notice if you want to stick your thumb in the negative X direction, you put your Y in, right? And as you curl your hands up, if you're in that negative direction, your hands sort of roll up, not down, and that will give you the positive Y direction. But I want to show you how this works. So you have K hat cross question mark equals minus I hat, right? So I want to show you something. I want to show you the pattern of cross products of unit vectors, and you'll see where we get this, how to look at this mathematically and sort of have a way to look at it without having to wonder if you're doing the right-hand rule right. And it's worth teaching you because it's really not hard. In fact, I'm sort of surprised there's parts of me, the right-hand rule, I guess, is technically faster, but there's parts of me that are surprised that we just don't teach it this way and drop the right-hand rule. I think we keep the right-hand rule because in Physics 2 it becomes important. There's a lot of different ones, and doing it by algebraically can be cumbersome. So that's probably why we keep it. So when you're looking at cross products, all right, once you there's a simple truth to life. You can define I and J any way you wish to, but once you define I hat and J hat, their cross product must be positive K hat. You can define X and Y any way you wish. They're arbitrary. But once you do, I cross J must be K. So K hat is defined as this cross product to remain positively orientated. Now I want you to notice something. As long as you follow this order, the cross product is positive. Let me show you what I mean. So if you go J, notice I, J, K. So J cross K equals I, right? So I, J, K. You'll notice it's like a cyclical. This would be sort of what we call a cyclical group. But you have I, J, K, J, K, I. As long as you're going in that order, and you can go around in a loop, you're going to be positive. And you'll notice the last one is K cross I equals J, right? I, J, K. It follows. Now, if you transfer these, right? You should note if you flip these around, you get a negative sign, and if you multiply any one of these by a negative, you get a negative sign, right? Or you can just flip it around. So if you have K cross negative I hat, that would just be I hat cross K. You can do that and get the same thing. They're equivalent. They're equal. But keeping track of just these three will tell you everything you need to know about the cross product. And here's where this gets kind of crazy. So they want C, the torque, to be in the negative Y direction. Negative J hat. So we want to cross K, cross so we know that we can't. So if we look at this, we can look down here and say, wait a minute, no, we have K. So here's the thing, right? We know these are all mutually perpendicular. If the radius vector is in the K hat direction and the final torque is in the J hat direction, we know that the force that causes it has to be in the I hat direction. It's got to be in the X direction. It's just a matter of whether it's positive or minus. But if we look here, we notice, and again, every book will tell you this. I've looked it up a million times. The only people who seem to think that even your book has this written down. The only time this seems to not be true is for this particular checkpoint. You'll see what I mean in a minute. So if you look here, you can see that this is wrong, so therefore you must have a negative here, right? Now it can be correct. So the force, the vector, according to a right-handed coordinate system, F should be in minus X direction. But you're going to see the book thinks it's in the positive X direction. And I've gone through it, and I can't find a legitimate reason for why the book thinks that. I think the book here is just messed up. Again, what I wrote for you is pretty standard stuff. They're claiming flat out here that K hat cross I hat equals minus J hat. This is not true. No math book in the world says this. And again, what I think they did to get that is I think they rotated their axes and didn't realize they had to reinitialize the cross products. Because that can happen. If you rotate incorrectly in 3 dimensions, you can actually think you're rotating, but you're flipping in a mirror, and that's not good. And that's what I think happened here. Okay? So, so if anyone can, so it's possible I missed a word. I miss words all the time. You know you miss words as if not more frequently. So maybe I'm missing something, but it says R in the positive Z direction, and then it wants the torque in the negative Y direction. That's got to be in the minus X direction for that to be true. All right, K cross I is going to be J. Okay, so let's move on. We've got a lot more to cover. I think we have another example, so this should be good. All right, so we have a figure, which I didn't show. I think it's in the next, right, it's in the next thing. So there, we'll see a figure. It'll be here. This is figure 11A, right? And we have three forces of magnitude equal to 2 newtons that act on a particle. The particle is in the xz plane at a point A, given by position vector r, where r is equal to 3 meters and theta is equal to 30 degrees. What is the torque about the origin due to each force? Okay, so you're going to want to do that, and let's look at the, so copy down the important information, and then we're going to look at the figure. Well, actually, I want you to try working on it first, and then we'll go over the figure, actually. I like that better. So keep in mind, right, T equals R cross F. And what I want you to do here is more try to set up the problem. So I'll give you a couple minutes to set up the problem, and then we will go over it and take a look at it from what we do. So I just want to give you a couple minutes to picture it, rather. It's okay if you don't picture it correctly. That's what we're trying to work on. I want you to try and picture it, and if you get it right, that's super great. If you don't, that's okay. We'll go through it and try to correct it, and you can think about what you were confused about. So I'll give you till 1:25 to do that. Oh, you want me to just try? Yeah, sure. Oh, you mean before we look at the picture? Okay, we can do that. Oh, you mean you want to draw the picture on the board? Yeah, I mean, if you want to go for it, you could try drawing it on the board there. That's all right. Yeah, no, that works. That's a good idea. All right, so does anyone want to draw? I think you guys can just select the drawing tool, can't you? I've seen you do it before. Nicholas, you want to give it a shot? I think I have to make you the presenter. All right, want to give it a shot drawing it?
I'm not sure my answer.
Okay, that's all right. Anyone want to give it a shot? Just let me know on the text and I'll make you the presenter, I guess. Okay. Well, I think this is, in looking at the problem, I think this is kind of the type of problem where you can sort of see how to set it up, but it might not be clear. So we've got three forces. They all have the same magnitude, and they act on a particle. So the particle is in the xz plane at a point A given by a position vector r equals 0. So you have to notice something here. You don't know which way the forces are acting. All you can draw is r. But r is kind of the hardest vector to draw. So you want to make, so in the way the book draws it here, and this is what I mean about being very careful, all right? I want you to notice the book is using rotated coordinates where they're going to call the vertical axis z. And this is probably why it was hard to drive, because generally we define this as x, y, and z, right? But for this problem, for this particular problem, since they want to look in an xz plane, they're going to call this x, z, and y. All right? Now I want you to notice that this is a weird coordinate system. All right? If you take x and curl into y, though, or take the cross product into y, your thumb points up. So z positive is correctly defined. But it's just a little bit odd to think about. That's y, not x. So, and this is where I think they made a mistake in the last checkpoint. I think they incorrectly defined the coordinate systems to get that part C. But the drawing would look something like this, where this angle would be 30 degrees. Okay? And that would be your angle. Now, of course, drawing in 3D is hard. And so I don't think I'm cruel enough to make you draw this too much, but learning to do it is useful. And so now you have your R in a much better drawing where you can see the force, the R vector. And then you have the forces, which you couldn't draw from the given information. I was hoping someone would say that in the chat or something like that, thinking about the problem, but okay. It's Friday. I get it. We're all tired. And you guys have an exam next week. So looking at this, we can see that we have these three forces, at least they're in the X, Y, and Z directions, and we have R. Now the first thing we're going to want to do is sort of move R, the tail of R, sort of put it at the tail of these force vectors. And then we'll sort of be able to rotate and look at things from this XZ plane. And that will make it easier to analyze the forces. So I want you to go through on your own part the work, and I'll delineate it here. This is the work for torque 1, right? And this is the work for torque 2. And I want you to try it and see if they're confusing or they make sense. Because it's funny, because I want to show you how to do it. If we were in class, I would show you how to do it, but this is one of those things where I can't put my hand on my screen and have you see it. So remember, our right-hand rule, put your hand on R. So do that first, right? And you can see what they're doing with their fingers. Try and emulate that. Curl towards vector. Curl towards GOWAR, the force, and then stick thumb out. And that'll give you the torque, or the direction of the torque. Okay? So I want you to play around with that and see if it makes sense. I want you to practice using the right-hand rule and basically ask me any questions if it doesn't make sense, so I can guide you along with it. Yeah. I'll give you 30 seconds here, and then I'm going forward, because that's just the numbers and stuff. And it's all in all the information here is actually in the next slide, because we only really care about the directions. Once we have that, the other stuff's pretty easy. You just add those, add those torque vectors together, and since they're in different, you just add them vectorally and express it as a rectangular vector. Okay. So yeah, you'll notice that with the numbers, the torque, you have 2 in the y direction. You have, and then you have this one in the x direction. It's in minus or positive x and minus z. So you'll have T3x in the I hat direction plus T2 minus T1, tau 1 or tau 2 minus tau 1 in the j hat direction. And then you'll have plus T3z in the k hat direction. All right, that's what your torque's going to look like and how you should express it. And you should be able to use triangles, again, to break this into x and z components. That should be pretty easy. That's chapter 3. You can add those numbers, and then you express it as a vector. All right, and that's how you do that final part of it. Okay. Let us continue into our realm of rolling motion. And now we get to one of my favorite subjects from Physics 1, which is angular momentum. All right, angular momentum is pretty cool, or would be one of my favorite subjects because we have so many awesome demonstrations for it. But of course, I can't do those. But angular momentum is a lot easier to visualize than linear momentum in a lot of ways, because you can look at rotate. It's easy to create a rotating closed system. And if any of you have a rotating chair that you have access to, if you're sitting on an office chair that rotates, and it rotates pretty easily and freely, you can experience the conservation of angular momentum yourself by getting two large heavy books, hold them out and start spinning slowly, and then bring the books into you and see what happens. You'll have some fun with that. You can do that during break. Angular momentum will, of course, because we're doing physics 1 and not astrophysics, we won't just hop into it, but we can see that much as we have, hold on, you know, we'll write L equals R cross P, but there's no reason to write L equals R cross P. We can derive this, or at least understand its connection to linear momentum. So remember that P, not P, sorry, F equals dp dt. Right? So if we look at this, if we go here to our torque, is going to equal R cross F, right? That's going to be equal to R cross dp dt. And we can write that as equal to d dt R cross P. So what's interesting here is that this gives us a new quantity. All right? And we're going to look at this because, again, we have that our force is equal to some time derivative, and we know that our analog to our rotational and rolling analog to force is torque. So when we look at torque, it is equal to the time derivative of something, right? And force is equal to the time derivative of something. Here in force, it's linear momentum. We can say, well, whatever this is, since torque is our analog to force, R cross P must be our angular analog to linear momentum. So we can call this quantity here R cross P. We'll just set this equal to a new vector. This will be equal to a resultant vector L. And we'll call this vector L linear momentum. And then instead of just writing it down, we now understand where it comes from. And we can also see directly that T will equal to dL dt, and that our analogies stay true, right? When comparing the torque to the force. Sorry, the torque to the force. All right? So we want to note here, again, that's a good way to understand and derive the equation, but we do want to make note of this point. It's an important one. It doesn't need to rotate about the axis, but the axis must be specified. All right? This is not axis independent. Your angular momentum changes if you change your origin, right? So your origin, you have angular momentum with respect to an origin. You don't have to be rotating around to have angular momentum. You can just be going by. But you'll have angular momentum at a certain point along your trajectory with respect to an origin. All right? It's a little, it's not really intuitive, but I'm hoping you can see it. And here you can see in the picture, you have R, you have P. This looks very similar to the torque problem, right? And we know that L is in the direction, in the Z direction. And if you do, if you take R cross P, you will get that positive direction. Now, a few of you might be looking at me going, no, Professor Tolan, that's not true at all. I put my hand on R, so put your hand right on R as it is, and you have to pick it up and go down. But remember, in order to take the cross products of vectors, right? You need to be able to get the angle between the vectors. Right now, you can't get that because in order to get the angle between two vectors, they have to be tail to tail. So you really need to you need to translate this vector like so. And now when you have this as r, translated, you'll notice phi is the angle between them, just like it is in our definition. And now if you put your hand on r and go towards p, you're going to be sticking that hand up, and you will see that the angular momentum is positive. So the unit of angular momentum is kilograms meters squared per second, or joule seconds. Okay. And I want you to try and play with that until you're convinced that the angular momentum is indeed in the positive z direction. All right. So I want to just, you don't have to go super fast, I guess is what I'm trying to say. All right. Everyone is convinced of the direction of L from the graph? I need a few yeses here.
Yes, Professor.
You're good? Okay. All right. So when we look at that, when we do that, we can notice that because we have a cross product, and I'll remind you up here that L, oh no, I'm back to blue. No one can see it. I'll remind you that L is equal to R cross P. So we can look at, when we look here, you'll notice that they're just using the definition of P is equal to mv to get that part here. And so you can clearly see that we just have our magnitude. We can figure out the same way. And we can also, again, use this line of action and or moment arm and line of action type way of looking at things. It's totally fine to do things this way. This I find, personally, I find very unhelpful. Some people, this makes total sense, and the other way doesn't make sense. So I would say practice both and see what works best for you. So let's take a look here at this figure. All right. We already said both these things. So in part A of the figure, particles 1 and 2 move around a point 0, right, an origin point. In part B, particles 3 and 4 travel along a straight lines at perpendicular distances of 4 and 2 meters from the point O. Particle 5 moves directly away from point O. All 5 particles have the same mass and the same constant speed. So we want to rank the particles according to the magnitudes of their angular momentum about the point O, greatest first. B, which particles have negative angular momentum about point 0. Okay? So, okay. So that should be some fun time to do. And keep in mind a few things as you're working on this. L equals R cross P, right? So the magnitude of L equals R P sine phi, and also equals RMV sine phi. And you'll also note that L equals the perpendicular distance times P, and it can also equal R times the perpendicular component of the momentum. Either one. I'm giving you all three things here. So take a look. I will give you the hint that it's possible for some to be equal. So if you have, so one way to do that, if we have 4 particles, one possible answer, I'm not saying the answer would be like 1, 3 equals 5, 2, 4, right? So you can do it like that if you're wondering if you think they're the same. That is not the correct answer, though, so don't write that down. I just made it up. I'm actually going to delete it so it doesn't confuse people. I just want to show you how to do it. All right, and hop to it. All right, any thoughts? All right, let's take a look. So 5, remember, I'm gonna, remember, Mina, you need not be rotating, right, to have angular momentum. So, so that's why we didn't learn about angular momentum in the last chapter, because it's not only pure rotation. Rotating systems do have angular momentum, and that's true. But you'll notice you have a perpendicular distance here. Hold on. You have a perpendicular distance here to the origin, right? So that's our perpendicular. And you definitely have a momentum. So when you multiply those two together, you're not going to get 0. But, yeah.
Question. So the perpendicular shouldn't be at that particular moment when the particle is like placed like on. So I would think that the line. Can I make the note here? Hold on for a second. Let me just gonna use the red color. So shouldn't be the particle here. So the distance would be here perpendicular to the region.
Well, I want you to notice both those perpendicular distances are the same. That never changes in the problem. So the distance to the origin from 3 has a perpendicular distance component and a horizontal component. The horizontal component is changing, but thankfully we don't care about that for our angular momentum. But you'll notice that the perpendicular component doesn't change, and that's the one we're interested in.
Oh, because in my mind it was like this. That's why
well, that's the total distance. That's the R vector. So for that part, and for that part, there's an R vector, right? So if you have the R vector, let me put in orange here.
Because in my mind it was moving.
Right? So the r vector will go like this, and there will be some angle there. But it's in a case like this where the perpendicular distance makes sense, because when comparing to everything else, it'll be easier which one's ahead and which one is not ahead. But what I want to show you is that there's an angle that's not equal to 0. There's a r vector, non-zero momentum vector, and a non-zero angle. So if all those things are non-zero, the L, whether it's bigger, the important part here is that L will not be equal to 0 here, right?
Mhm.
That's what I want you to see first. To compare it, it's easier to look at it in terms of the parallel distance, just because we don't have any other information. And that's often the case. That's the only time I use this representation, is when the problem is just set up in terms of these things. Yeah, I'll jump right to it. But if it's not, which they usually aren't, because this is overall the easier way to set up a problem, then I'll just use those parallel distances. I'm just going to erase the non-parallel distances here. Right? So when looking at that, you can see that 1 and 3, for instance, have the same parallel distance. They have opposite momentums, but I believe we're looking for magnitude, right? According to magnitudes. So we can see that. So what it comes down to is getting a sense of this parallel distance. We can see that 2 and 4 will have the same parallel distance, but it would be smaller than 1 and 3. So we have 2 equals 4. We have, no, hold on. Yeah, 2 equals 4. Before that, we have 1 and 3 are bigger. And then, of course, the angle that this makes is there's 0 parallel or perpendicular distance. R perpendicular is 0. Another way to look at that is the angle between R and the momentum is 0. They're parallel. So then you have 5. Okay? So everyone so I5 is 0, but R10, no, 5 isn't in the middle. We're just looking at magnitude. So 5 is at the end. Okay? So does that make sense? All right. So we're going to go on break. I'll be back a little after 10 after, and we'll finish up, okay? Okay, I'm back. Well, you always have to take into consideration the angle, but it's the, in this case, you're sort of looking at just the perpendicular distance. So recognizing that that's the only part that contributes, that's all you have to really take into account. Camera would like to do that. Oh, did I turn the camera off? You know, it just, okay. All right. Okay. So let's move on with our conversation of angular momentum. A topic that is, oh, we didn't do part B. Oops. Let's do part B. No, I did part A. So B, which of the particles have a negative angular momentum? Well, there you want to take your R vector, right, and cross it in and see which one goes. But the trick here is that once you get that R vector, you have to whatchamacallit, you have to put the tail to the tail. So you have to translate your R vector up to where your momentum vector is, and then you'll be able to see which one you have going on there. So if we look here, 1 is pretty clearly, you can also look and see how it's moving. You'll notice 1 is moving counterclockwise around the circle, which is usually positive. 2 is moving clockwise, so that's negative. The right-hand rule tells you that. And if you look up here at 3, right, they're sort of pointing in opposite directions. That'll sort of give you the idea that at that point, they're switched. So it's going to be 3 is going to be negative and 2 is going to be negative, assuming, of course, that the clockwise direction, or the counterclockwise direction, rather, is positive. And that's where we get 2 and 3 from. Okay? So there's my trusty pencil. Let us move forward. Okay, so now we already sort of did this, but we already saw from our brief derivation earlier that we can very easily get T is equal to dl dt. I'm not going to do it again. You can just go back in the video and look at it. We've already derived this, but we can see the relation there. We defined L in terms of this relation. So the torque and angular momentum must be defined with respect to the same point, usually the origin, but that's important. You have to set up consistent systems. Origins and things like that can't go all over the place. Everything's got to be a self-consistent system. And, oh, we're covering something here. I want to be sure it's not something too important. And, oh, well, we already noted the similarity. We already did this derivation and showed how these two were related. So, like I said, you can go back and look at that. But one thing we can note is that the vector sum of all the torques acting on a particle is equal to the time rate of change of the angular momentum. So another way to say that is the sum of the torques, I, is equal to the net torque is equal to I alpha, which also equals dl dt. So you see you have a lot of stuff you can do here. Okay? All right. So we have our checkpoint 5. All right, so the figure here shows a position vector r of a particle, right? We've got that there. And we have 4 choices for the direction of a force that is to accelerate the particle, okay? All 4 choices lie in the xy plane. Now, this looks 3-dimensional, but it's not. You have to look at this as 2-dimensional. So these are not a 90-degree angle, for instance. All right, it can be hard to visualize because we've been doing so much in 3D, but this is a 2D problem. All right, so we want to rank according to the magnitude of the time rate of change, dl dt, they produce in the angular momentum particle about the origin 0, greatest first. All right, so we want to see which one of these will lead to the largest angular momentum. All right, so we have R and we have F. So they all have the same R, so let's try and see which one will maximize dB dt. And the trick there is to see how is F. If F increases, what happens to L? And you'll notice we're measuring not the L part, but the rate of change. So we know that dL dt is equal to R cross F. So we can see that whatever orientation maximizes this will give us the biggest dL dt, or the biggest torque. All right, because that's what dL dt is. So try and do this one. See if you can figure it out. Remember, it's in 2 dimensions. So think about when R cross F is maximum, when is it minimum, and when are you in between? Okay, let's take a look. So we'll want to notice, the first thing to notice is the angle between all of these. So we can almost say R. We have R is the same for each one, right? And then we want to look at F1, F2, F3, and F4. So we'll want to look at theta and then sine theta. All right. So if we look here at F1, we have what looks to be an intermediate angle, right? So we'll just call this theta. That's okay. That's not helpful. And that will be sine theta, will just be sine theta. So not super helpful, but you know, not super great either. You'd extend the tail out here to your R vector, right? And so this would be your theta that we're talking about, this angle here. But let's erase that. So, but we know that angle is bigger than 0 and less than 90. So that tells us something. And I just erased everything, didn't I? Let me make that table again. So we have the same R vector. Yeah, Mina.
Sorry, just a clarification. The angle. This is as we did with the cross products in previous chapters, when we have to select the angle that's the least between the two vectors.
Right. So what I did there, and that's exactly what I did. I moved R up to here for F1, right? So this is R, and this is the angle between F1 and R.
Got it. Thank you.
Okay? Nope, no problem. So when we look here, let me make my chart again. F1, F2, F3, and F4. That's one value, and then we have our, so that's the F, the theta, and the sine theta. All right, so with F1, we saw it's just going to be some angle, and we don't get much information there. We know it's not a max up. Basically, the only information we have is that it's an intermediate value. Okay? So now let's look at F2. F2, you'll notice, is exactly parallel. It lies right on top of R. Right? So the angle between F2 and F and R, where R and F2 is 0. And the sine of 0 is 0. Right?
Mm-hmm.
So we go to F3. F3, the angle between R and F3, we can look here, is going to be 90.
Mm-hmm.
Right?
And the sine of 90 is 1.
Sine of 90 is 1. And for F4, the angle is 180 degrees, or pi, and the sine of 180 degrees is 0.
Mm-hmm.
Right? So we can see here that F2 and the torques, we can see that dl dt 2 equals dl dt 4. Those are both 0, right? And then we know that F3 represents a maximum value, and F1 is bigger than the minimum, but less than the maximum. That's all we know because it's intermediate. So for part A, we have F1, F2, no, not, I'm sorry, F3. I'm writing it correctly. Don't listen to what I say, just pay attention to what I write. F2 and equals F4.
Mm-hmm.
Maximal, intermediate, and the other ones. Now, before I give everything away, which choice results in a negative rate of change about the origin? I gotta look and think. So the way to look at that here. So everyone, look at part A for a minute. Are there any questions on part A before we go to part B?
No.
Okay, good. Because I think part B is pretty obvious. That should be a hint. I'm hoping it's obvious. If you look here,
When we say negative rate, we mean moving clockwise, no?
right, exactly.
So the F3.
Exactly. Very good, Mina. Or Fatima. Who was talking? I can't. Oh no, it was Mina.
Mina being guilty.
So I can't recognize everyone by voice. I have to look at the little thing who's talking.
No worries.
So when we look at this, we'll notice we have this component, and you just have to ask yourself, is this going to cause, pretend it is rotating, right? Is this going to cause a clockwise or counterclockwise rotation? And you'll notice that the only ones that would cause rotation are F1 and F3. It would be opposite. F3 tends to go clockwise. So F3 is going to cause the negative motion. Okay? So hopefully that makes sense and that is good. All right. We got a lot of checkpoints in this chapter. They sort of serve as our examples because, again, there's sort of a lot to see. If you're worrying about doing intense examples, chapter 12 is almost the opposite. There's one idea only that takes about a minute and a half to go over, and then we'll do almost a whole day of examples, or 2 hours of examples that are very in-depth. So you will get there, but or we will get there, but you just have to be a little patient. Okay. So now we want to get to angular momentum of rigid bodies. All right. So we can sum the angular momentum of particles to find the angular momentum of systems of particles. All right, just like we had before. And so you'll notice that we go from a particle notation of these script L's to a big L for a system of particles or a rigid body. All right. And then you'll notice that the net torque is just the time derivative of the total angular momentum of the system, which is just the sum of the angular momentums of the individual particles. All right. So this is very much just a statement that what you can apply to one carries over to the whole. All right. Now, you'll note, I want to note that they've noted this 5 times in this chapter. That should let you know that it's important and that it confuses students regularly. All right. It says, note that the torque and the angular momentum must be measured relative to the same origin. They keep talking about keeping your origins and your systems consistent. It's important. All right. If the center of mass is accelerating, then that origin must be the center of mass. If the center of mass is accelerating, then at the origin, that must be the center of mass. Okay. I don't really know what they're trying to get at there. We can find the angular momentum of a rigid body through summation. So you'll look at that here, and you'll notice that when we look at for a rigid body, as confusing as all this might be, the math makes it very simple. All right, because you'll notice that this term here is just your moment of inertia. All right, and we can just write that the angular momentum of a rigid body with a fixed axis is going to be I omega. Okay, so the center of mass stuff probably has to do with finding that center of mass and using the parallel axis theorem, because that's the one thing with moment of inertias that we like to be able to take advantage of frequently, is using that that parallel axis theorem to find different moments of inertia from the center of mass moment of inertia. And you can see we still have a corresponding table between relational, translational, and rotational motion. But we want to be aware that this is more general and, of course, can also apply to rolling motion. Okay, so that's sort of, I believe that's our final whatchamacallit, correspondence table. So basically we've taken 2 chapters to do for rotational and rolling motion what we did in 1 chapter for translational. Okay, so if it seems like there's a lot, there is. And are there a lot of weird-ass problems you can ask? You betcha. And you should be doing those for homework. Okay, so this brings us to another checkpoint. Now, in the figure here, you have a disk, a hoop, and a solid sphere. Now, the classic way of asking this question is to ask you guys, to ask students, I'm sorry, just a long week, to put these at the top of a ramp. So let's sort of look at that. You put a disk. Let's make a ramp. Oh, you know what? I'm going to use lines. Lines are better. So let's make a ramp. And at the top of this ramp, you put the disk, the hoop, and the sphere. And they all have the same mass, and they're all set to at the same place. They all have the same radius, and you set them in motion. And the question is, who wins the race down the hoop or down the ramp? Now, your intuition might tell you, well, wait a minute, they all have the same mass, and they all are moving under gravity, therefore they should all hit at the same time. If you dropped all three of them, this would be true. But they're rolling here, and they'll have angular momentum. And as we recall, L, oh no, I have to, as we recall here, L equals the moment of inertia times the angular velocity. Now, looking up in a table, because that's what you should do, let's look it up really quick. We've got the angular, we've got I disk. Is equal to, we're going to call that a hoop. Well, we wrote disk down first, so let's see, a disk. We're going to call that, hold on, my mouse is not cooperating.
MR squared.
No, I know. I'm just looking at my table. So for the disk, it's solid cylinder or disk about the center. Right. So I'm just looking at my thing. My text is small. And again, like I said, I don't have stuff like this memorized. So about our center axis, disk will be equal to 1/2 mr squared, right? And a hoop, I will be equal to mr squared.
Okay.
And for the sphere, we have 2/5 mr squared. Okay, so what we want to know here to answer that question, which one wins the race, we want to rank the objects according to their angular momentum about the central axis. Okay, now you'll notice they have the same force will act on each object. So this can be a little tricky. So I'll give you a couple minutes to work on this one. All right, so you'll notice, so remember there's two parts here. So the question isn't who will win the race down. That'll actually be answered by B. But think about A. Are the forces different here? And are the radiuses different? All right. So radius and mass are all the same, and the forces are all the same. So I misled you a little. All the information I gave you is pertinent to part B, not really to part A. Part A asks about the angular momentum, right? And so remember, the angular momentum, the torque, is going to be equal to R cross F, right? All the F's are the same, all the R's are all the same, so all the torque's all the same. So if T, so that means that if T equals dL dt, right, L equals the integral of T dt, yeah? So that means that they're all acting within the same time scales, so all of the L's will have to be the same. So L disk equals L hoop equals L sphere. Okay, now for part B, now we want to use this formula, and you'll notice that while the angular momentums are all constant, the individual moment of inertias are all different, right? So when we look at them here, we can see that the hoop is the greatest, is greater than it's the greatest. The one in the middle is going to be the sphere, is greater than I disk, right? And we can see here that if you, the bigger your I, the lower your omega, right? And conversely, the lower the I, the higher the omega. So it wants us to rank the greatest angular speed will be the lowest moment of inertia. So omega disk will be greater than omega sphere, will be greater than omega hoop. Okay? So hoop disk sphere, or disk sphere hoop. At least that's how I get it. Let's see. Let me see if I messed it up. I did mess it up. Look at that. Sphere disk hoop is the correct one. So did I misread the moment of inertia? That is a possibility.
So can I celebrate?
You can celebrate, absolutely. Let me see here. How did I'm curious how I messed it up though. 2/5 is, oh, I did mess it up because 2/5 is 0.4, and in my mind,
Yes.
I read it as 0.6. So
0.5.
yeah, no, one half. This is 0.5. This is 0.4.
0.4.
Yeah. So for the sphere, I read, but in my mind, I do that sometimes. I put the wrong. I think one number and write the other. So yeah. No, you can definitely celebrate. So the error was I just misdid 2/5. It can happen to anybody. Moments like these where I'm glad you're taking the test and not me. So let's just flip these around. Get it correct. Hoop, the disk, and the sphere. I knew that sounded wrong when I said it. So that will mean that we have to change these. And we can see the sphere and the disk. Now we're good. Yeah. And that was just a stupid math error on my part. That's okay. It happens. All right. Always check your math. That's the lesson there. Okay, I think we're good here. All right. So there we go. Now, angular momentum, just like linear momentum, is a conserved quantity. All right. And again, like I told you, I hope some of you did that with the, that was B. Mina, the first one was they were all the same. Good. So if any of you did the thing with the book, if we're able to rotate and bring it in, you will notice that you span faster. And if you are spinning fast, you can put your arms out and you'll slow down considerably. And if you have heavier books, you'll slow down even more. So if someone wants to put you on a tire swing and spin you really fast, the best thing you could have is 2 giant weights, and then just bring them out and put them out, and then the tire will slow down, and then you can jump off. Yeah, I had a bad experience on a tire swing when I was a kid. So much like we had with energy and momentum, P initial equals P final equals constant, and energy initial equals energy final equals constant. These were both true for closed systems. All right, closed systems or isolated systems. You'll notice that comes up here again too. And we have the same thing. All right, and this establishes conservation of angular momentum. So we can see that it's a little more useful in this form here, where we have I omega initial plus I initial omega initial equals I final omega final. This is a very useful form of the conservation of angular momentum. And we want to look at these 2 star points here. So if the net external torque acting on its system is 0, the angular momentum is conserved, no matter what changes take place within the system. Let's read that again, but make it look more like chapter 9. So if the net external force acting on a system is 0, the linear momentum of the system remains constant no matter what takes place within the system. I want you to notice those read the same, right? And we're using our analogs to make the same arguments in the same way. And of course, there's since these are vector equations, they're equivalent to the 3 corresponding scalar equations. This means we can separate the axis and write, just like we did for momentum, that if the component of the net external torque on a system along a certain axis is 0, then the component of the angular momentum of the system along that axis cannot change, no matter what changes take place within the system. That's pretty powerful. That means that you can now say that linear, just like linear momentum, angular momentum is conserved along each axis. All right. And you'll notice that your moment of inertia changes with your geometry. So by just changing your geometry, you can change your moment of inertia and affect your angular speed. Okay. So now we have some examples. So the student spinning on the stool. This was the one I was hoping you could all find a way to do, or some of you could. A springboard diver, when they jump off and rotate, I would say normally that if you watch the Olympics and the high diving, you'll see conservation of angular momentum in action. But we won't have a Summer Olympics this year. Very sad, but very necessary. And the long jumper one, let's see. The angular momentum caused by the torque during the initial jump can be transferred to the rotation of the arms by windmilling them, keeping the jumper upright. Okay, that's a lot more motion than I'm used to. So any of you who are into the long jump or track and field, you can look at that one. But of course, we will have another checkpoint to look at this conservation. So a rhinoceros beetle or murder wasp, if you want to be contemporary, rides the rim of a small disk that rotates like a merry-go-round. All right. If the beetle or murder wasp or death wasp, I don't know what they're calling those things, those giant wasps. If the beetle crawls towards the center of the disk, do the following, each relative to the central axis, increase, decrease, or remain the same for the beetle disk system. All right, so we want to look at the rotational inertia, angular momentum, and angular speed. All right, and this as the beetle goes from one end to the other. So you can sort of look at it like this. Let's draw the pictures. Circle 1, circle 2. We want to move circle 2 so that it's at least even. And this is our initial and final. I know they're not the same size, but pretend they are. So in the initial one, the beetle or killer wasp is there. And in the final, they're here at the center. All right, so we want to know what's happening to I, omega, L, and omega as this process goes from initial to final, right? Will the moment of inertia increase, decrease, or stay the same? The angular momentum increase, decrease, or stay the same? And will the angular velocity increase, decrease, or angular velocity increase, decrease, or stay the same? This is physics, Mina. The wasp is stuck. And we're not looking at that system. And that would be a dynamic system because it would be imparting momentum onto the disk. And bad things can happen there. Okay. I'm waiting for B and C. Well, let's take a look. So remember, we're in an isolated system. So B is actually the easiest one to answer first. And L initial equals I omega equals L final. All right, and we can, another way to write this is that I initial, omega initial equals I final, omega final. So the total angular momentum actually stays the same. All right, now, yeah. Mina.
I'm sorry, someone's asked. It stays the same even though the radius keeps decreasing as the B goes towards the
Well,
center.
remember, we're not. So here's you are looking at the angular momentum of the beetle, where you have to look at the angular momentum of the beetle disk system. We're not looking at just the beetle.
Oh, okay, got it. All right.
Yeah. So this is the system angular momentum of the isolated disk beetle system, not just the beetle. Okay.
Got it. Okay, thank you.
So in that sense, the momentum stays the same. Now, as the beetle goes from the edge, from the initial to the final, I will indeed get smaller. So this will decrease. And that will lead the angular momentum to increase. Because again, if you have a decrease in one of these variables, you have to increase the other. Okay? And we can see that there. Decrease remains the same, increases. All right? Now, for our final topic when it comes to gyroscope, when it comes to this, is a lot more fun to do in lab. And I don't even usually lecture this section. I just do it in lab. But we can't see it, so if you look up bike wheel processing on YouTube, I'll leave you to do that on your own for the last couple minutes. But I'll just sort of explain what we're looking at very quick. So if you imagine I had a giant bicycle wheel like we have in lab, and I were to hold it out on a string and just let it go, it would fall and hit me in the leg, right? And you would all laugh. I would be in pain. It would be kind of amusing. However, if you spin that gyroscope and you expect it to be even more fun because now it'll be spinning and it'll cut into me, what you will find is that it won't do that. It'll actually precess around the axis. It'll almost seem to float in air. And it does this because it's bound by conservation of angular momentum. All right? So let's look here. With it spinning, it'll have a torque in this direction equal to dl dt, where this is spinning. And what we'll see is that the angular momentum of the rapidly spinning gyroscope is equal to I omega. And the torque can only change direction, or can only change the direction of L, not its magnitude. So because the torque, because you have that angular momentum going, all the torque can do is change the direction, and that causes it to precess around the axis. All right, instead of toppling over. So it's actually, it happens just because of conservation of angular momentum, but it is a far more spectacular thing to see in real life than it is not in real life. So this is exactly, so the precession rate, I forgot, is given here. You can figure out that precession rate for a sufficiently rapid spin. Valid for gyroscope and an angle to the horizontal as well. Yeah, okay, like a top, for instance. So that's it for chapter 11, and that's what I hope to get through this week, so I don't feel bad about our shortened lecture yesterday. Chapter 12 takes about 2.5 to 3 hours to do, so it's not a good chapter to just sort of start on. Doing it in all its own day might make it a whole one-day affair. So I'm going to stop recording, and that's the end of lecture. Are there any questions before I stop recording about the lecture? We're going to answer other questions after I stop recording, like the test and other things. All right. So let's